Hey guys, it's Carrie, and this is the answer key video for homework number 3, unit 8. So the sequence below shows a pattern. Is the above sequence geometric or arithmetic? Sorry, I read that out of order, but it's the same thing. So it looks like the pattern is plus 3 to get from each term to the next. Because it's additive, it's an arithmetic pattern, or arithmetic sequence. Determine the common ratio or common difference. Because it's an arithmetic sequence, the common difference is plus 3. Determine a recursive formula for the nth term in the sequence. So here I'm going to switch down to the space down here. A recursive formula is one that depends on the previous value. So a recursive formula always has two parts. I start at 5, and to get to the nth term, I take the previous term and I add 3 to it. In this set of rules, start at 5 and then add 3 to the previous value to get the next, completely defines this list of numbers. For part D, it says determine an explicit formula for the nth term in the sequence. So an explicit formula is one where it's not dependent on the previous value, it's a straight jump up. So to get from the fifth term to the 100th, or sorry, from the first term to the 100th term, I'm going to put this in like a little thought bubble because this is what I think about as I come up with the general formula for n. Okay, cool. So A100, to get to the 100th term, I would start at the 5th term, and I'd have to add 3 to get from the 1st to the 100th. That's 99 steps. So I'd have to add 3 99 times. So really, what that means for the nth term is to get to the nth term, start at 5 and add 3, one fewer than whatever term number you're trying to get to. So if I'm trying to get to 100, it's 99. If I'm trying to get to n, it's n minus 1. So this is our explicit formula. Since this formula is independent of the previous value, it works for all n values. N equals 1 would give you 5, and etc. Lastly, A42, you just plug into the formula, so you get 5 plus 3 times 42 minus 1. A42 is equal to 5 plus 3 times 41, and 3 times 41 is 123. So you get A42 equals 128. That's a plus sign there. Thanks. Okay. Next up, we have a sequence below. This sequence is multiplicative. It's times 4 each time. So it's geometric. The common ratio is 4. A recursive formula for this sequence would be start at 5, so A1 equals 5, and a recursive sequence is always dependent on the previous value. So we do A sub n is equal to 4 times the previous value. All right, our recursive sequence is completely set. For part D, we're looking for an explicit formula. So just like before, we can think about this using a specific number. So I'll draw that thought bubble like we had before. So this is what we're thinking about as we come up with the general sequence. Oh wow, my smiley faces are not so great, but this is what we're thinking about. So we have A sub 100 would be equal to, we'll start at 5. To get to the 100th one, I'd have to multiply by 4 a bunch of times. In fact, to get from 1 to 100 is 99 steps in between, so we'd have to multiply by 4 99 times. Times 4 times 4 times 4 times 4 times 4 times 4, that becomes the 99th power. So in general, we get that A sub n is equal to 5 times 4 to the 1 less than whatever number we were trying to get up to, because there's one fewer step to get from 1 to that value. I'm going to let you guys find A sub 10, so I'll leave that as a blank. Figure it out. Next up, we're looking at some sums. So determine S sub 10, determine the sum S sub 10 of the 10 terms in the sequence shown below. So one way to do this is to actually add these all up in your calculator, but that's not very clever, and it might take me some time. So we learned in class a clever way to do this. So we know that S sub 10 is going to be the sum 2 plus 8 plus 14 plus 20 plus 26 plus all the way up to 44 plus 50 plus 56. Writing that sum forwards and writing that sum backwards wouldn't change the overall value. So we also have that S sub 10 is equal to 56 plus 44 plus, oops, I missed one. 56 plus 50 plus 44 plus all the way down to, well, these are the last three, so I'm going to write the first three, 14, 8, and 2. All right, so the clever part about writing it forwards and backwards like this is if you add term by term, let's see what we get. S sub 10 plus S sub 10 yields 2S sub 10 on this side. Over here we get, adding column by column, 2 plus 56 is 58, 8 plus 50 is 58, 14 plus 44 is 58, and we can see because each one of these is going up by 6, and each one of these is going down by 6, that all of these sums will result in 58. So because these are all the same number, there's an easier way to add these together. So we get 2S sub 10 is equal to, well, because there were 10 terms to start with, we'll have 10 58s here. So 2S sub 10 is equal to 10 times 58. And then the last step would be to actually do the calculations. So 2S sub 10 is equal to 580. Divide by 2 to solve for a single S sub 10, a single sum, and we get S sub 10 is equal to 290. And so to me, that's a lot more rewarding than actually adding up these numbers on the calculator. However, in the future, we're going to see that it's actually completely necessary because we'll be adding up way more than 10 terms. So I'm going to leave problem 4 for you, and problem 5 is a little bit trickier, so let me do that one. So consider the sequence, 5, 10, 15, 20. Determine the 19th and 20th term of the sequence. So a sequence is not the sum yet. A sequence is just the list of numbers. So my instinct here is it would be very, it'd make things a lot easier if we could jump straight to the 19th and 20th without determining all the terms in between. That makes me think explicit formula. So to get from 5 to 10, 10 to 15, 15 to 20, it looks like it's an arithmetic sequence with a common difference of plus 5. So an explicit formula for our sequence could be to get to the nth value, start at 5 and add 5 n minus 1 times. So the two values that concern us are a sub 19, so start at 5 and add 5 18 times. That would give us a sub 19 is equal to 5 plus 90. That equals 95. So a sub 19 is 95. And then for a sub 20, maybe I can use the recursive idea for this one. If I know the 19th one is 95, I know the 20th one will just be plus 5 more. So if this is 95, then the 20th one after, would just be 100. So a sub 20 is equal to 100. So now that we've got these terms, we can ask a harder question, which is, can we add up all of these terms? So even though we're missing a bunch of them in the middle, we definitely can. So let's write it out. S sub 20 is equal to 5 plus 10 plus all the way up to 95 plus 100. And because this is a sub 20 and this is a sub 1, we can see that there are 20 terms in this sum. Similar to what we saw before, the sum would be the exact same if we wrote it backwards. So let me, in pink, write the sum backwards. So it'll be 100 plus 95 plus all the way down to 10 plus 5. So if we use the same trick that we saw before, adding the forwards and backwards version of the sum, we see that we get 2s sub 20 is equal to 105 plus 105 plus 105 plus 105. So we have a lot of 105s there. Because we're adding up the first 20 terms, and each column adds to 105, what we have is we've got 20 times 105. So 2s sub 20 is equal to, let's see, this might be a bit beyond me here, 2,000, wow. I wish I had my calculator. 20 times 105. I'm running over to the calculator. This is actually a pretty easy problem, and I'm shocked that I can't do it, but I'm on the spot. 2,100, nice. That's what I thought it was. I can say that, but no one can prove me wrong, I guess. Divide by 2. Thanks, Stephanie. S sub 20 is equal to 1,050. So we add up the first 20 terms of the sequence, we get 1,050. What's really nice about that is we didn't even need to find all the terms. So it's a major shortcut for us to be able to do this using the forward-backwards trick because we don't actually have to find all of the values in between. This trick forwards and